And so for our last talk of this session, we have Peter Samuelson. And thank you very much, Peter, for speaking, and go ahead.
Okay, well, thank you for the invitation and for organizing this special session. And also thanks to everybody for sticking around till the end. Right, so I'm also going to be talking about BMW algebras, basically. So, oops. Right, so I'm going to talk about the skein algebras of the torus. And this is based on joint papers with Hugh Morton and Alex Pokorny. So you can see the outline I wrote here. So there's, first I'll talk about just a very brief introduction and say what my notation is. And I'll say what skein algebras are. Then I describe these two skein algebras for the torus. I'll talk about the elliptic-Hall algebra a little bit. So this is in the direction of categorification. All the skein algebra stuff really is at the decategorified level. And then I'll make a couple technical comments about the generators that we found. Okay. So the way I like to think about skein relations is that they come from representation theory of quantum groups. So this is a story I think everybody here knows. This quantum groups gives you this R matrix, which is a map from V tensor W to W tensor V. And these R matrices satisfy some linear relations. And that's what skein relations are. Okay. So historically, these were really first used to define invariance of knots in S3. But I was sort of raised as an algebraist, and so I like algebras instead of polynomials. So I like to think of skein relations as something that input a surface and output an algebra. And I'll say what the algebra structure in a second. So there's, today I wanted to talk about two versions of skein relations. The first one is the Humphrey skein relations. So this is the normalization that I'm using. So you take the difference of two crossings on one side and it's equal to a constant times the resolution. And then there's a framing variable that I'll call V. So you can remove a full twist in a strand at an expense of this constant. And then the unknot is equal to some constant. Okay. So these relations make sense inside of any oriented three manifold. And so the skein module of a three manifold is just, sorry, maybe let me move it over here. So this is, links in the three manifold, M, oops, sorry, links in M, framed links, modulo the skein relations. So this is just some vector space in general. Okay. If M is just S3, then this vector space is one-dimensional, and the image of a knot or link is one of these classical knot polynomials. Well, I guess they're quantum, not classical. Right. So the other version of skein relations I'm going to use is the Kauffman skein relation. So these are the relations that give you the BMW algebra. I'll say a bit more about that later. And morally, they're similar, but they're a little bit more complicated. When you take the difference of the two types of crossings, you get two terms instead of one, which actually is a lot more complicated. But the skein module is defined in the same way. It's just the relations are different. We're using unoriented links instead of oriented ones in the Humphrey case. So if the three manifold I am looking at has its additional structure, then the skein module has extra structure too. So if the three manifold is of the form surface cross interval, then I can glue together two copies of this three manifold and get the same one back. So that turns the skein module into an algebra. So I can multiply two links by putting one on top of the other. So these algebras tend to be interesting, but they're also very poorly understood, except in small examples. Right. So the first thing I'll talk about is how, in examples, how can we understand these algebras from the point of view of an algebraist? So how can I find a presentation of these algebras? So so far, well, okay, it's known for the disk and for the annulus. Those were known for a while. For the torus, these were only understood more recently. So I'll describe them both at once. This is really two theorems. Each of these algebras has generators that are labeled by points in z squared. So each generator is a sum of knots, or sum of links. So you should think of this x as measuring their homology class, roughly. So these generators satisfy some simple commutation relations. So if I take the commutator of px and py, I get some constant times p of x plus y. So this, I wrote out this first example of this here. So if I pick x and y to be simple, like 1, 0 and 0, 1, then they represent these two curves here. So P10 has homology class 1, 0. So I'm saying when I multiply P10 times P01, I put this horizontal curve on top of the vertical curve. And this square is the torus. I can't draw an actual torus, so I draw a square instead. And then when I multiply in the other order, I switch the crossing. So you can see, actually, let me scroll up, that this diagram with squares looks exactly like this diagram with circles. So I can remove the crossing and I get this constant here. And that's exactly this constant times P11. So that's the first example of this relation here. Okay. Similarly, and right, so that was a paper a few years ago with Hugh Morton. A year or two ago, we did the BMW case. So in the BMW case, there are also generators indexed by x and z squared. These are unoriented diagrams. So there's a relation here that says dx equals d minus x. That's just saying that these generators are defined in terms of unoriented curves. So that relation is not very interesting. Well, yeah. The more interesting one is this one here. So it says the commutator of dx and dy is a constant times dx plus y minus dx minus y. So I can do exactly the same example here. I haven't written it out, but you can imagine what happens. In the BMW case, let me scroll up so you can see the relations again. If I take the left-hand side here, these are unoriented curves. I can replace it with the right-hand side of the skein relation, and I get exactly the relation that I wrote here. Okay. So the theorems are saying that these are presentations of these two skein algebras. Oh, and this D that I was writing is the determinant of this matrix. So you put X and Y are both elements in Z squared. So you put them in a matrix and take the determinant. Okay, so I should maybe point out that these relations, actually I'm going to say that in a second. These relations are simpler than you might expect if you do some experimentation. The real key is, how do you define the generators? So the sort of idea is that if you pick complicated but correct generators, then the relations are simple.
Can I ask a quick question?
Yeah.
So I'm supposed to think about these links on a torus as, well, there's some correspondence to points in Z2. How is that picture P11?
Oh, because it's
one.
it's the simple closed curve with homology class 1, 1.
Oh, that's right. Yes, this is on a torus.
Yeah, it's on a torus. Yeah, when you first look at it, it looks contractible, but
yeah, sorry, you said that already. Thank you.
Right. Yeah, and in general, if X is primitive, what I wrote doesn't make any sense. It's not compatible with what I said before. So if X, if the vector has relatively prime entries, then these generators are the simple closed curve of that, of that class, homology class. So that's true for 1, 0, 0, 1, 1, 1. Right. But for something like P22, the generator is more complicated. There's no simple closed curve, and you have to make a better choice. Right. So I'll say more about that later. But one thing that surprised me as we were figuring this out is that there's actually a uniform definition for generators in both cases, which isn't something I expected. They still seem mysterious. I still don't know why this definition works, but maybe someone else has better ideas. But I wanted to order things in the other way, so I'll say more about some details of this theorem later, but I wanted to say a little bit about categorification first, although there's not much I can say, but I'll say a little bit. So, but to do that, I have to sort of shift gears. So now I want to talk about the elliptic Hall algebra briefly. This is completely different, really. So the Hall algebra is a way of constructing an algebra from a category, an abelian category, instead of from a surface. So let's suppose that we have an abelian category over this finite field. You can do some more general things, but I'll stick with this case because it's all that I need. And we need some finiteness assumptions. So we'll assume that Hom spaces and X1 spaces are finite dimensional. In this case, we can define an algebra. So it's an algebra over Q, and it has a basis given by isomorphism classes of objects. So the basis is, as a vector space, it's not that interesting, but the multiplication is interesting. So the multiplication uses the abelian structure in the category. So if I want to multiply two objects, then what I'll do is just write out the structure constants. So m times n is automatically a sum over e of e times some number. And what's the number? I've written it here. So I look at all sub-objects of E so that the sub-object is isomorphic to M and the quotient is isomorphic to N. So I'm basically counting the ways that E appears as an extension of n by m. Because of these finiteness assumptions that I made here, so there's a finite field and finite dimensional Hom and X1s. This is a finite number. And the number of non-zero terms is also finite. It's not obvious that this is associative, but it's not too hard to prove. It's a good homework exercise. Yeah, at least in this case. If you want to, well, yeah, it's not too bad to prove. Right. So, I guess one of the first ways that these Hall algebras were related to representation theory was a theorem of Ringel. He showed that if you, I haven't written this theorem, but if you, if the abelian category you start with is modules over a quiver, say an ADE quiver, then the Hall algebra is the positive part of the quantum group of that type. Okay. So Hall algebras give a sort of intrinsic way of constructing quantum groups and putting in the Q's in the right way. So that was in the earlier mid-90s. Berben and Schiffman in the early 2000s computed the Hall algebra coming from an elliptic curve. So if we have an elliptic curve smooth over a finite field, we can take its category of coherent sheaves. Okay. And it satisfies these two finiteness assumptions. So we can take its Hall algebra. And there's a technical note. There's we really want to take a subalgebra. The whole Hall algebra is too big, so we need to take a subalgebra. But I won't say more about that. Just a technical note. So Berben and Schiffman described this algebra in a very explicit way. Okay, sorry, there's another technical note here. Maybe I should say, maybe I shouldn't. So they defined an algebra E, the elliptic Hall algebra. It depends on two parameters, Q and T. And they defined it by hand. It's generated by elements U sub x, where x is in z squared, modulo some explicit relations. These relations are complicated, so I won't write them down. And they depend on these two parameters, Q and T. And what they did, they showed that this algebra sort of gives a universal description of all Hall algebras of coherent sheaves over elliptic curves, sort of all at once. So precisely, they said, if you pick the curve x, then you can pick two constants in C. So really, I need to replace this Q with a C. So that if you specialize Q and T to be these constants, then you get the elliptic Hall, or then you get the Hall algebra of this curve x. Okay. So there's a plus here. Technically, that's like a positive subalgebra. It's the analog of the Borel subalgebra. That's what the plus means. So this is really a remarkable theorem, I would say, because you're computing all these. Well, yeah, it's a hard computation, I think. They also constructed an SL2Z action on this algebra without the plus. So using their theorem, we combined their theorem with ours. we can show that if you specialize these two parameters q and t to be equal, the algebra you get is isomorphic to the Homfley skein algebra of the torus. And the SL2C actions agree. So these, the proof is just sort of brute force. You look at their relations and specialize the parameters and then compare to ours. So it's, well, but it works. So I wanted to say that because I wanted to ask a question about the Homfley case that I don't know. So this parameter specialization, so really I drew all the arrows backwards here. I should go the other way. So if you specialize q and t to be equal, there's several places where this same type of specialization shows up. So, or maybe I should say, if I start with one parameter and introduce the second one, that's the analog of going from skein theoretic invariance to not homological invariance. So there's a lot of subtlety here. Another analogy which fits into the same picture, if I had looked at the Kauffman bracket skein algebra of the torus, adding the second parameter gives me what's called the spherical double affine Heck algebra of type SL2. Or in terms of combinatorics, this is like going from Schur functions to Macdonald functions or Macdonald polynomials. So one question here I don't know the answer to is what's the analog in this set of analogies? What replaces, what goes on the right-hand side if I start with the Kauffman skein algebra? And I don't know. And I don't exactly know the state of the art for categorification, but you can say, you can also ask about, you know, BMW homology if it does exist. It should be related to this answer for the Kauffman skein algebra of the torus. Okay. Right. So that was a little bit about categorification. I didn't, as I said, I didn't say very much. Maybe someday I can. Next, I wanted to say a little bit about these generators. And I said some of this out loud already. So let me just scroll up like this. So their presentations are simpler than you would guess, or than I would guess. Than I guessed at first after, you know, playing around with pictures. And the point is that if you pick generators in the right way, it simplifies the relations. So how do you pick them in the right way? So this goes through a different skein algebra that it's already been mentioned, I think. So a different way of getting an algebra using skein theory is to have, say, a square with some marked points on each side, or on two sides. If you have the same number of marked points, then you can stack them together and you get an algebra. So you take the relative skein of the square, and you look at tangles in that modulo the skein relations. So in this way, you can construct the Heck algebra in type A, or the BMW algebra, well, using the Kauffman skein relations. Okay. Both of these algebras have symmetrizers. So these are uniquely defined by these two conditions. They should be an idempotent, and they should absorb crossings at the expense of a constant. And these uniquely characterize the symmetrizers. In both cases, you can take a diagram in the square and close it to get a diagram in the annulus. So this is the closure map from the algebra to the skein algebra of the annulus. So either the Heck algebra or the BMW algebra So really, I'm describing both cases at once. So you can take these symmetrizers, which are defined uniquely, and close them, and get some unique elements, which I've written as f hat n. N refers to the number of strands in the box. So the skein algebra of the annulus is commutative. So you can take power series with coefficients in the skein algebra, and then make this an identity here. So I'm using the right-hand side to define the left-hand side. So I should put a colon here to be precise. Okay, so you might recognize this power series identity from combinatorics. On the left-hand side, you would put the power sums, and on the right-hand side, you would put the elementary, I forget, I think it's the e's. So there's this identity is true in the type A symmetric functions. That's been known for a while. I don't exactly know what type B or BCD symmetric functions are exactly, but whatever that is should be isomorphic to the skein of the annulus, BMW skein of the annulus. And for some reason, the same power series identity gives nice generators, and I don't know why. So I don't know why this identity, it seems to make sense in all types and not just type A. Oh, okay, yeah, H's or E's, maybe it's H's, you're probably right. Right. Yeah, well. Well, in any case, some of these formulas are cartoon formulas. So if you squint hard enough, E and H look the same. Okay, I'm almost out of time. So, this is how we define the generators. Now, there's a key identity these generators satisfy that I wanted to mention. So this identity occurs in a different algebra. So this is like the relative skein algebra of the annulus with one point on each side. So you look at tangles in this diagram that begin and end on these dots, and you allow closed loops. So this actually is a commutative algebra. Where the product comes from nesting annuli. So here's some examples of elements in here. There are some invertible elements like this A. And then if you have an element in the closed skein algebra of the annulus, there's two ways you can put it into this algebra, script A. You can put it below everything or above everything, like in these two pictures. So that's alpha of X and beta of X. So this KB means Kauffman bracket. I removed that from previous parts of the talk, but not here. So in the Homfley case, this generator satisfies this relation. If you put PK, the difference of PK above the identity and below the identity is equal to a constant times A to the K. So this is really the fundamental identity that these generators satisfy. And then in the Kauffman case, it's basically the same thing. I should have written D instead of P, but whatever. So in both of these cases, the K equals 1 case is the skein relation. And then when K is bigger, it's something that you have to prove. And maybe just one sentence about the proof for the torus. So if you want to prove relation between two of these generators that we picked, you prove a couple special cases. One of them is this fundamental identity. The other one is just between two simple closed curves, and you can just be stubborn. And then there's some induction you can do about using SL2Z action and some more arguments. Right, so I'm out of time, so I'll stop here.
Thanks. Let's thank Peter. And does anybody have any questions?
I have a question, Peter. Great talk, by the way, about the relation about the alpha PK minus beta PK. I thought, am I confusing? I thought, there was a something like that where the P, instead of a P, you have like them all going over, then all going over but one, then all going over but two, and all going over but three, and like, how does that fit into what you're saying? What am I misremembering there?
I think that's the definition of PK. So there's
okay.
There's this
From
way
your
to define
picture with
it.
the alpha and the betas, I didn't see that.
Yeah, it looks almost the same. So in this case, you're putting PK on this closed loop around the alpha. I mean around the annulus. Yeah, but I don't know how that diagrammatic definition. I don't know if it interacts nicely with this identity. I think the proof goes through some power series tricks, or at least the proof that Hugh found a long time ago. So I don't actually know a diagrammatic proof of this identity, and I also don't know a diagrammatic definition of, in the BMW case, of these generators.
Okay, I think I know a diagrammatic. Well, I don't know if we're talking about the same thing, but I might know in the Homfly case a diagrammatic proof of that.
Oh, huh.
I have some. I can send you some old pictures with some scribbles, but we can see if they're the same or not.
Oh, that would be nice, actually.
Yeah, I was fiddling with Kevin Walker and we were doing, and you do an inductive argument, smoothing crossings, and really keeping track of stuff, and things cancel.
Yeah, you have to do it pretty carefully. Yeah, I did the first. Yeah, I can't.
Yeah, I just assumed your proof of it was diagrammatic. I mean, when the paper came out, I'm like, oh look. No,
yeah.
or maybe I'm talking about old work of Hugh Morton and Eiston or something. Maybe I have the wrong. I might be confused about what these things stand for.
I think his proof of this identity was using power series, and our proof in the BMW case is also power series.
Oh, okay. I'll try to dig up these old pictures then.
Yeah, that would be interesting.
I had a question, Peter, about the same equation. In my paper with Matt on computing triplet-graded non-homology for torus links for the full twist, we have this nice short exact sequence in the Hecke category between putting a Jones-Wenzel projector above a strand and a Jones-Wenzel projector below a strand, and the third term is a Jones-Wenzel projector of one bigger size using all the strands. How does that interplay with this equation here? Like, I don't really understand how PK is. I mean, I saw the formula, but I don't feel it. So,
Yeah, so I think the way the proof goes in this case is that of this thing, you can translate this equation into into a recurrence relations for the Jones-Wenzel projectors. And I think it's that recurrence relation. So you do some power series trick to go from this equation to take the log or exponentiate or whatever, and do that stuff. Yeah, so these PKs, I don't know what they would mean homologically. There's a
right. Is there a complex for that? Yeah.
I'm sure there's a complex for them. Actually, it's something it'll be something that's close to this. I think that's P1, something like that, really close to P1. And then I think if you put, wait, how does it go? I forget how it goes. There's another way you can write them, which is like a cycle.
Yeah, that complex that you just wrote down is notoriously difficult.
Yeah, yeah, that's I've heard that. And then in here, I think you told me that in Oregon actually. I think here you put powers of the juicy Smurfy elements as some. Oops. I think this is PK up to some constant.
I see. So these are the power sums in uses Murphy's.
Yeah,
And that's why P1 is the okay, I understand.
but you have to have a cycle here. But yeah,
Yes, yes, yes.
yeah.
Okay, are there any more questions for Peter?
I have a small, very silly question. Have you thought about like what if you wanted to do this for like an affine BMW algebra? Is there a natural way of extending it to the affine setting, or does it not even make sense?
You mean trying to use, well, the affine BMW algebra, you can think of, like one way to think of it is using this picture, but you put on some more dots, right?
I guess that's part of my question. Yeah. How would you?
I mean, I think the affine BMW algebra you can define using this tangles in this diagram modulo the BMW relations. But then, but there's also closed, it's a little different because there's also closed loops in here. So this algebra is a lot bigger.
Okay.
I have another question that I'm not sure how's the best way to ask it, but so I guess maybe here you have this algebra curly A with like one boundary point on the inside and outside. If you consider the algebra with like more, like say n, I don't know, points on the inside and outside, is there a similar commutation relation between like, P on the outside versus P, P above versus P underneath the identity?
Yeah, you get a sum of juicy Smurfy elements or powers. You can, I mean, this relation, so I guess part of the point is this, there's only one term on the right-hand side.
Yeah.
So you can pull it through one strand at a time. And each time you just get the one term left over. So
Oh, I see, of course.
so you get a sum of these juicy Smurfy elements,
Awesome.
which, okay, I don't know why it appears in both places. That's weird.
Well, the PK, your picture on the right confuses me. I thought it would have just been, you take the like the sort of mixed braid lifts of the n cycle, not purely positive, not purely negative, but kind of some interpolation between, and you add those up. I thought that would be PK.
I think that's the same as this. If you write the JMs correctly, oh, oops. There's two indices here, or there should be two. Yeah. So yeah, I think that what you were describing is the same as this if you get the indices right. So the power is the K, and then juicy Smurfy 1 up to K, I think. Because
I thought K would just be the number of strands, and then that's uses Murphy to the power 1. But anyway, it doesn't matter. But
oh, I'm sorry. You're right. I'm sorry. I was mixing up two identities.
But I guess if you commute it, but that K is coming from this other thing, the right-hand side of this commutation relation. Sorry, very confusing.
I was confused. And that would make it very confusing. Right. So if you wanted to do this commutation relation in the Heck algebra with n strands, you would get the sum of n juicy Smurfy elements all raised to each raised to the power k. Sorry. So this is the n equals 1 because there's one dot. Sorry.
Okay, so if we have no more questions for Peter, let's thank him one more time.